Hi everyone, this is going to be a demonstration of how we use our new exponential probability functions to answer questions like this. So we have an expected life in hours of an incandescent light bulb, can be considered to be a random variable with an exponential distribution for which lambda equals 1 over 900. Part A, for how many hours would you expect the incandescent bulb to work? Well, using our previous result, we found that the expected value of x was 1 over lambda. So we have a very straightforward calculation. They gave us that lambda was 1 over 900, and so we would say the expected lifetime for our incandescent bulb is 900 hours. They're talking hours, yes, that's part A. Easy as that. Part B, find the probability that a particular light bulb will last at least 1,000 hours. Be careful with the phrase at least 1,000 hours. So we want probability that x, our random variable. Now if I say at least, I'm happy with 1,000 hours or more. So x must be greater than or equal to 1,000. So this is the integral from 1,000 to infinity of our probability function. And our probability function, remember, is defined as, where can I write this? Let's go across here. Remember our probability function that x equals a certain x is equal to lambda e to the negative lambda x. That was our function. So we would have 1 over 900 e to the power of negative 1 over 900 by x, and because we're taking an integral we need dx. Now we could perform this manually, or we could use technology depending on which of the exam papers we were looking at. So remember, doing this with technology would be child's play. Actually, let's do it manually first and then we'll check the answer. So we want the integral. Well, 1 over 900 is a constant. Now I would have e to the negative 1 over 900x divided by negative 1 over 900. Would have been much easier if I wrote lambda everywhere, wouldn't it? So that 1 over 900 cancels with that 1 over 900, and I'm integrating from 1,000 to infinity. This is looking a bit messy, isn't it? So I'd have negative e to the power of, this is negative infinity over 900, subtract negative e to the power of, that would be negative 1,000 over 900. Now that first value of course comes to 0, and this is just plus e to the power of negative, and that would be 10 over 9. And that can certainly be calculated. So here we are. Let's just clear all that stuff away. Now all I really need to do is go e to the power of negative 10 over 9. And I get the answer 0.329. Or 32.9%. So there is a 32, roughly, very roughly, a 1 in 3 chance that my light bulb would last for 1,000 hours or longer. So there you have it. Now I did say if this was a tech active exam, you would have been able to literally just write the formula, the expression, and then you could have just popped straight over here onto the calculator. Let's just take all that away to make it empty. Remember, maths, then integral. Now my function is the first thing I enter, and it is, well, let's just write it as e to the power of negative x over 900. So that's my power, and then all of this would be over 900. Now right arrow moves me to my terminals, and I want to go from 1000 to infinity. There is no such thing as an infinity key, but if we just put a large number. Now you might be tempted to put something like 1 by 10 to the power 99. You could end up with an internal memory overflow error or something. So let's just put something really, really large, like 100 million or something, and we'll hopefully. Whoops! I think I upset the calculator. That did not turn out as expected. I probably overdid it with the value of. There we go. Let's just take away a couple of those zeros. So 100,000. Let's see what we go this time. Oh, there we go. So it was. I did get a funny answer because I put a number there that basically upset the internal memory workings of the calculator. So I know that's not 1,000 to infinity, but it is giving us the same answer because we're going to a very large number, which is practically, as far as the probability function is concerned, it's 0 from there on out. So there's a little trap to worry about with your technology, and I suppose here my upper limit is 100 times the lower limit, so that's going to be to 3 figures anyway. That's going to be the same answer, and then I could literally just write the answer down. Oh look, using the calculator, this was 0.329, 32.9%. There's your first calculation. Now part C and part D. A compact fluorescent lasts about 8 times longer than an incandescent. Right, so they're telling me the expected lifetime is 5 times 900. Indirectly, they're telling me that lambda is different for this type of bulb. And what is the chance the fluorescent will last at least 1200 hours? Okay, so I'll do this one. Part C. They're telling me for this new type of bulb, the expected lifetime is 5 times the incandescent, which was, did they say 5 or 8? Let me go back. I might have got mixed up then. No, 8 times. 8 times. So that is 7,200 hours for the expected value. And they want the probability that it lasts for 1,200 hours or more. So here we go. The probability that x is greater or equal to 1,200 hours seems like it's going to be pretty likely to be true if the expected value is this. It would be the integral from 7,200 to infinity of, now I need lambda, don't I? Remember, lambda is the inverse of the expected value, so 1 over 7,200. That's going to be a small number. 1 over 7,200 e to the power of negative x over 7,200 dx. This time I might just go straight for the technological solution. I'll pretend I'm doing a tech active exam. So I could literally just go back here and change my numbers. We'll make that one 1,200. I'll leave my upper limit as it is. That one will have to be 7,200, as will this one, 7,200. Cross your fingers, everyone. There we go. We seem to have an 84.6% chance. So 0.846. 84.6% chance that the light bulb will last for 1,200 hours or more. Now, when the expected lifetime is 7,200, you might seem, well, that's roughly 15% of them will fail less than 1,200 hours of lifetime. So you'd feel a little bit unlucky if that happened, I suppose, but that's probability distributions. You can never quite tell an individual result. You can only talk in terms of the distribution. So yes, the expected value might be out here at 7,200, and from there on out might be 84.6%. But there certainly will be some outcomes that occur in that. Oh, sorry, did I say 7,200? 7,200 was the expected. But we were talking about 1,200, weren't we? And so, yep, 7,200 200 is the expected lifetime. From 1200 or more, 84%. But yes, there certainly will be some unlucky people that get a light bulb that lasts less than 1200 hours. I don't think I'll do the last one, it's much the same. That's a nice little example of how we can use this type of mathematics in practical questions. Thanks for watching.